So my name is Máté Ferenc Nagy-Egri, and I work in the Wigner GPU laboratory. And what I would like to talk about today is research that I've been conducting with some Polish colleagues in search of continuous gravitational waves. And I would want to give a very short one-slide, only media, overview of gravitational waves and testing a hypothesis that we came up with regarding the employed precision in the search pipeline and our motivation of why we chose OpenCL to accelerate the computations. And there are quite a few slides on the challenges on using OpenCL for this particular purpose. And then I'll show our results with some future directions that we are hoping to take. So gravitational waves, if you open any your favorite news source, then you most likely know what it is. When there are dense astronomical objects either revolving around each other, which is the black holes or the binary systems, they emit gravitational waves. And also small systems which do not merge there are two sources of continuous waves. One is the wide binary systems, when there are two objects that revolve around each other but they don't fall into each other. And the other is non-axis symmetric objects. So if a rotating object is not spherically symmetric, so it has some kind of oblique shape, but the rotation of axis is not the symmetry axis, it doesn't fall straight into the symmetric axis, then there is a wobble as the object rotates, and that also emits gravitational waves. Now the biggest difference between the two is that the amplitude of the waves are much, much larger in the black hole mergers or the binary systems, especially towards the end of their lifetime when they are really close to each other and they are rotating at a high speed. Then the amplitude of the gravitational waves which we can detect on Earth magnify, and typically it is the last few seconds of this merging that we can detect. And the last few seconds, I mean 3, 5, 7 seconds is what we can detect currently. If we want to detect continuous waves, then the observation time has to be a lot longer, so not a few seconds, but a few days. And if the observation time is long enough, then the signal-to-noise ratio, even though the amplitude of the signal is much, much smaller than the actual noise of our detector, which it picks up, the long detection time helps us actually find the signal. And the way to detect the two, the math behind the two, are very much different. Especially in the merger systems, the actual inclination angle of the signal doesn't really change much in 3 seconds time, so the Earth doesn't rotate much in 3 seconds time. But if the observation time is a few days long and the detector does go around a few times, the signal which it detects throughout the 2 days has to be modulated, and that is accounted for in the search pipeline and in the math. So that's about the physics with no math equations. Our hypothesis was usually scientific computations default to using double precision just because it is cheap, especially on CPUs. They are hardware accelerated, and we seldom have to fear rounding errors. There are a few corner cases with ill-conditioned matrices and things like that, but usually we are fine doing double precision. And we don't even think about it that often, especially when playing around with algorithms. But what do we sacrifice when we just say blanket default to double precision? Well, we double the bandwidth that we're using, and we're also losing out on a lot of architectures which are not that much double precision friendly, especially GPUs, and GPUs, and especially the low-end GPUs, the low power, and even the consumer graphics cards are not that forgiving for double precision. And we ask the question that, is it really necessary to do everything in double? And of course, the question arises because if a GPU programmer comes, everything is, and has a hammer, everything is a nail. So must we really do double precision? Of course, GPU programmers like to think that they have a minigun and not a hammer in their hand. But choosing OpenCL was, well, we wanted to choose OpenCL because it's portable, so we can target many architectures, even FPGAs if we wanted to, but but we can target multi-core CPUs, any vendor GPU out there, and we can also target architectures that don't even exist yet. So if somebody is reading the news, then you might know that Intel is bound to release their dedicated graphics cards, which are bound to ship in 2020. And Intel is fully behind OpenCL and SYCL. So we know that if I write my code in OpenCL today, I can run it a year from now on an architecture that doesn't even exist yet. And it might just be that that architecture performs better for my kind of workload. And also, generic GPU optimizations, primarily trying to make the best use of local memory. It also makes half a decent CPU implementations, because trying to squeeze the work into a few kilobytes of memory, which are reused heavily, this is actually a poor man's cache optimization. So if I write just portable, trying to be portably friendly to all GPU architectures, and I write my code that way, it's actually quite a decent CPU parallel implementation. The pipeline which we accelerated looks something like this on paper. There's some initialization part when we read the positions and the properties of the detectors. And then there are two nested loops. One is over the sky coordinates. So this is an all-sky search. So we try to find the gravitational wave, may it come from any direction. And we calculate some amplitude and phase modulations depending on which detector is at what position of the sky, and that that's what we have to modulate our data with, and there's a starting phase. There is some FFT involved in this part, and also spline interpolation in this part. And then there's a spin down loop when we loop over the frequency of the signal that we are trying to find. So, and the size of these loops, both the sky loops and the spin down loops, they are our spatial and our spectral resolution. And in decent all-sky searches, there are roughly 3,000 sky loops, sky coordinates which we loop over, which are chosen carefully for the FFT interpolation part in the spin-down loop, and roughly 200 different frequencies. And once at the end of the loop, we record some signal candidates, which there's a peak detection part there. We are trying to find peaks in the spectral space, and we record those maximums which we find above a threshold. Those will be our candidates, and then we loop over to another sky position. And there was so the pipeline was already finished, and it was written in Linux-only, GCC-only code. And my first attempt was, initially what I did is that I ported it to ISO C11 so that the host code is actually portable, not just the device OpenCL code, but the host code is also portable. And porting to C11 in a warning-free manner is actually a nightmare. If anyone has done it, then they should know. Especially the secure extensions to the C runtime isn't a success story in terms of portability. I consciously did not want to turn off the warnings on any of the compilers because they did help finding bugs, which the application worked accidentally, and the warnings helped find those bugs. The POSIX extensions are ubiquitous, and also complex numbers on Windows is, again, not a success story with using Microsoft's compiler. It makes the code look very ugly. I'll show just a little bit of that. Also, I had, because we wanted to do multi-GPU and scan multiple sky coordinates at the same time, we had to introduce some parallelism into the host code as well. And the code was not designed in a way to do that. So first I had to isolate state and remove all the global variables and remove stateful functions at const correctness and then identify how to parallelize the code. There is two levels of parallelism. One is the coarse grain, which is choosing the sky coordinates and then dedicate one GPU to processing one sky coordinate. And once the GPU is finished, give another sky coordinate to the GPU. And for this, we needed a thread pool implementation. Well, OpenMP just happens to be an efficient thread pool implementation. And it's also portable, so that's what we used on that regard. And for the fine-grained data parallelism, we used OpenCL. Now the sad part. Some things that we struggle with is buggy runtimes. For example, there is a kernel cache bug in the NVIDIA runtime which has been reported 4 years ago and it has still not been fixed. NVIDIA caches the compiled kernels, so if somebody compiles the very same kernel again, then it just returns the compiled result. The problem is that the cache system disregards the included header files in the kernels. And if somebody is using configuration headers, even inside the kernels, which we do because we wanted to tweak the actual precision used on various parts of the pipeline, it was only the configuration headers that changed, but the work remained the same. And the NVIDIA runtime gave back an outdated binary for me, which resulted in strange output. AMD on Windows, again, is not a success story. They haven't touched their runtime for a long time. Apple declared OpenCL deprecated, which is a very strange move, and nobody quite understands why they did it. Well, of course, okay, don't get into that. And the most common libraries which somebody would use, like BLAS and FFT, they are not actively developed. They do get bug fixes, but they don't get new features. And we did happen to stumble upon a bug in both CL-BLAS and CL-FFT because we use both of them. CL-BLAS for an inner product and CL-FFT for the Fourier transforms. This is the entry point or the main function, what you call to get an FFT transform in CL-FFT. And the API was designed for multi-GPU usage, so if I had one work, I could give it to multiple GPUs and it would just magically happen. One FFT executed on multiple devices. However, even though the API was designed this way, it was never implemented, and it does return an error if I try to give it, not equal to 1. That should be on number of queues and events. If that's not equal to 1, then then it gives me back an error. And also in the documentation, it reads that you can create contexts that are associated with multiple devices, but CL-FFT will only use a single device from that context. And that was what I wanted to do. I had one context with multiple devices, which it says later that it's not valid, but the paragraph suggests that if you want to execute on one device, then you can still execute on one device. It will get the job done. And in fact, on AMD platforms, that is what happens. So if I have a context with multiple devices and I give it a command queue from pointing to one of the devices, it will happen what one might expect. And on other runtimes, it will corrupt the stack. And if anyone has debugged stack corruption, then yes, that's a sad story. Not an easy thing to do. Another challenge is writing type generic code in OpenCL. It involves using a lot of macros, macro if-defs around the actual types and the actual functions to invoke buffers, erase the store type, which sometimes helps, sometimes doesn't help that much. This is, for example, the invocation of the spline interpolation. All the types which come in and come out, they are type defs in a configuration header. And the Linux code is fairly simple and straightforward because because it is using the built-in complex types which can be cast to one another. But if the compiler doesn't know what complex float and complex double is, then you have to do those castings manually and conditionally. If these macros, which is this spline double and FFT double, they are different, then sometimes you have to do conversions, sometimes you don't have to do conversions. And especially all the operations, you don't have the nice operator syntax of plus and multiplication, but you have to use functions, again with different names because it is C and you don't have function overload. So the code which are in between those if-defs, if-else, and if, I don't want to show because it's very ugly. And the problem is that it's not just the host code, but OpenCL too, because OpenCL has reserved the complex keyword as of version 1.0, and I don't know how a compute language can make do without complex types. It's beyond me, but still, OpenCL does not have complex numbers inside kernels. So the kernel code actually looks, so the kernel code looks like this worst case scenario. And also there are no matrices, which again I don't get, but okay, I didn't need matrices for this calculation. And also to make the previous talks touched upon this, that to make efficient use of the GPU, you have most of the runtimes like if you do deep pipelining, so you issue all your commands up front as much as you can, and then let the runtime schedule the commands as it sees fit or best. And if somebody has like a chatty algorithm, like launch something on the device and wait for it to finish, then launch the second calculation, wait for it to finish and issue, there's going to be a lot of idle times, which we've seen in the previous talk. So the entire pipeline is, every pipeline stage has its own events, and the dependency graph is built accordingly. And I give maximum freedom for the runtime to schedule anything which can already be executed. It's free to do so. There's a dependency graph, do your thing, and let me know when it's finished. And for the results in terms of precision, these are preliminary results. Our gut feeling was actually right, that on this diagram we can see the x-axis is the signal to noise ratio, and our threshold is made at 6, which is an arbitrary number, that anything below 6 we treat as a noise, and above that it might be a signal. And on the y-axis, it's an absolutely arbitrary norm measuring the relative error to the reference implementation of the algorithm. And we can see which was serial. And we can see that the gray numbers, the numbers are I did make them larger, I don't know why it's not that large. So the gray color is when everything is done in float. The orange color is when everything is stored in float, but we calculate in double precision. So we don't pay for the bandwidth cost, only for the compute cost, which on GPUs we can usually do because we are always memory limited. So we load things in float, so that we don't use that much bandwidth, but we calculate in double, so that we don't get the rounding errors. But when we commit to memory, then again we write the results in float. And blue is when everything is calculated in double, which was the original algorithm as well. It did everything in double. And we can see that that for the very high this was an artificially injected signal into the data. For the very high signal-to-noise ratio, we see that the relative error compared to the reference implementation, it is well below 0.1%, which is a success. And as the signal-to-noise ratio decreases, the error also starts to increase. But yes, if we do calculations less precisely, then we cannot reproduce noise. So this is expected to be that way. And of course, runtimes, because we implemented the pipeline in GPU. So we should, if it's a data parallel algorithm, we should get speedups. And these numbers were coming from this laptop here. It's a desktop Ryzen 7 and an RX 580 AMD GPU inside, so high-end CPU, mid-range GPU. And the original ISO C11 calculation took, this is all in seconds, the all-sky search. It took roughly 9,000 seconds. And going to just using the same CPU, but with the OpenCL implementation, using it as a CPU device, we see that there isn't that much difference in calculating only in float and storing float but calculating double. So these numbers, that the orange and the gray bars are almost the same, indicate that yes, in fact, we are memory or bandwidth limited and not compute limited. And when we change to actually storing in double, then we can see longer run times. And because we're using OpenCL, we can use the CPU and the GPU at the same time, and it does gain benefits. Although I do have to say that there is a limitation implemented that when both kinds of devices are used, then a few cores are reserved to issue commands to the GPU. So I did implement device fission into the code, and I reserve one core for every GPU that is used, so the system has time to issue commands to the GPU. Now this is a somewhat beefier workstation node with RX Vega cards, so higher end GPUs, and there are actually two of them. And the runtimes do show that using multiple GPUs is a gain. Although when one starts to use multiple GPUs, it can be seen that even though that a few cores are dedicated to issuing commands on the GPU, we do net lose performance when we try to use the GPUs and the CPUs simultaneously. So that few milliseconds in which the GPU sits idle because the memory bus is being used or the cache has a higher load, it does show. So when one starts to use many GPUs, it's just not worth the effort to use the CPU simultaneously. And showing this workstation next to an NVIDIA server, which had 4 GPUs inside, an ASUS server, using 4 GPUs does show its benefits. What is kind of interesting which is to be expected. What is kind of interesting in this comparison is that the CPU runtime, both in especially in the ISO C11 implementation, but also using the CPU device, I would have expected that this dual socket Intel server would be faster, but that is not the case. So this shows that even in the CPU parallel code, I suspect that CLFFT does not handle well multi-socket nodes, and the code itself is not NUMA aware. So when one starts to use multiple CPUs in the same system, then the QPI becomes, it does have its cost of using the QPI if the code is not aware of it. We also run an Intel Phi node, and it does show that it does require a lot of tuning if one wishes to use an Intel Phi node. Future directions. To get type genericity, we want to move from OpenCL to SYCL, so we can use templates instead of macros. And we also get a few high-quality machine learning libraries like SYCL-ML and SYCL-DNN, which were not mentioned in the morning slides. Not to mention that we can use any arbitrary type. We get stud complex, which is portable, and we'll get more readable, robust code. What else do we gain? That this entire monstrosity of building the events and building the dependency graph, this all goes away when we're using SYCL, because SYCL takes care of this for us, building the dependency graph depending on buffer usage. And we want to add machine learning to it so we can filter the false positives of the algorithm. And just a very short amendment, if somebody wants to jump in, there is a random number generator on our GitHub site, which 2 talks ago or 3 talks ago was not mentioned. It's written in SYCL, it's open source, it's on GitHub, so you can click on the link and check it out. There are 2 random number generators implemented initially, both STL SYCL compatible. It's currently in alpha, beta-ish stage. And if you want to help me push it through the finish line with a few tests and implement the one last missing function, a jumping algorithm, which is half-baked, then feel free to submit a pull request, and 1.0 can go on it. Okay, thank you for your attention.
Okay, thank you, Máté. Questions? People getting tired. I would have a question. So once you did the calculation with the GPU card and the GPU plus CPU cards, did you use the existing data from the gravitational wave, or it was just a kind of sample what you generated?
It was generated noise with injected signal.
Have you tried with the real data?
I have, yes.
And
the results are largely the same. So it works on both artificial input data and both real detector data.
So when the time is coming when it will goes to the real database to search for something which is unknown yet? So I mean, when do you want to do as a factory work in real data, I would say? Well,
I could test it on real data as the Open Science Lab of Virgo and LIGO. There is publicly available data of all the gravitational wave detections up so far. They are mostly the compact binaries. I'm not sure that there is a publicly available continuous wave data. I will have to check.
I don't think so. Otherwise we would
but
know.
I can get not public data as well, but
okay.
For other people, only the public data is.
So this is you say, it's a kind of ongoing activity?
Yes.
Yeah.
Yes, absolutely.
Okay. Anybody else? Okay. So let's thanks Máté again.